While everyone debates colonizing Mars, there's a planet that could actually support life, sitting just 4 light-years away. Proxima b. It's in the habitable zone. It might have liquid water. Scientists call it the most important exoplanet discovery we've ever made, and humanity will never reach it. Proxima b made headlines in 2016 as the closest exoplanet to Earth. It sits in the habitable zone of the nearest star to our Sun, just over 4 light-years away. The discovery felt monumental because finally we had a neighbor, a rocky planet, possibly with an atmosphere close enough that we could actually talk about reaching it. Except we can't. 4 light-years might sound close in cosmic terms. Still, it represents a barrier so absolute that no current technology, no realistic future breakthrough, and no amount of funding can overcome it. This isn't pessimism, it's physics. And understanding why Proxima b is unreachable tells us something profound about our place in the universe. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. Multiply that by 4. That's how far Proxima b sits from Earth. To put this in perspective, Voyager 1, humanity's fastest spacecraft, has been traveling since 1977 at 17 kilometers per second. At that speed, it would take over 70,000 years to reach Proxima Centauri. Let's say we build something 10 times faster. That's still 7,000 years. 100 times faster, 700 years. The problem doesn't scale in our favor. To make the journey in a human lifetime, you'd need to reach approximately 10% of the speed of light. That's 30,000 kilometers per second, and this is where everything falls apart. Chemical rockets are fundamentally limited. They work by carrying fuel and burning it, but the faster you want to go, the more fuel you need. More fuel means more mass. More mass means you need even more fuel. The equation defeats itself. Nuclear propulsion is better, but still insufficient. Even fusion rockets, which don't exist yet, would take decades to accelerate to a fraction of light speed. And fusion is the optimistic scenario. Antimatter sounds promising because it converts mass directly into energy with perfect efficiency, but we can only produce antimatter in microscopic quantities. Creating a single gram would require more energy than humanity generates in a year. There's no scaling path. The most realistic proposal on the table is laser sail propulsion. Projects like Breakthrough Starshot envision using ground-based lasers to push lightweight probes to 20% light speed. The probe would reach Proxima b in about 20 years, but this requires lasers powerful enough to be visible across light years, sails thinner than paper but stronger than steel, and targeting precision we've never achieved. It's theoretically possible, it's just nowhere near ready. Here's the real killer. Energy requirements scale exponentially as you approach light speed. At 10% light speed, you're dealing with enormous kinetic energy. At 50%, relativistic effects kick in, and the energy needed starts approaching infinity. Einstein's equations have been unwavering on this point. Even a small probe needs massive energy to accelerate. Add instruments, communication systems, power supply, shielding, and the mass multiplies. Every kilogram added increases the energy cost dramatically. And then there's deceleration. You can't just fly by Proxima b at 20% light speed and learn anything useful. You need to slow down. That means carrying fuel for braking, which adds more mass, or using the destination star's light, which is far too dim. Neither option is practical. Let's say we somehow send a probe. It takes 20 years to arrive. Now it needs to transmit data back to Earth. That signal takes 4 years to reach us. If something goes wrong, we won't know for 4 years. If we send a fix, it takes another 4 years to arrive. Round-trip communication, 8 years minimum. This means total autonomy. The spacecraft has to make every decision itself for decades. No human intervention, no troubleshooting, and it has to work perfectly in an environment we've never tested, bombarded by radiation that degrades electronics over time. Data transmission at interstellar distances is its own nightmare. Signals weaken as they spread out. To send meaningful data back, you need powerful transmitters and large antennas. Both add mass, both consume power, both increase complexity. The space between stars contains gas, dust, and high-energy particles. At low speeds, this doesn't matter. At 10% light speed, a single speck of dust hits like a bomb. The kinetic energy of a collision scales with velocity squared. Every microgram particle becomes deadly. Shielding helps, but only to a point. Too much shielding adds too much mass, and at extreme speeds, the shield itself becomes a problem. Collisions generate heat and radiation. The faster you go, the worse it gets. Then there's cosmic radiation, high-energy particles from distant supernova constantly streaming through the galaxy. On Earth, our magnetic field and atmosphere protect us. In deep space, there's nothing. Electronics can be hardened, but radiation damage accumulates. Over the decades, systems fail. Proxima Centauri itself is a problem. It's a red dwarf, smaller and cooler than our Sun, but it's also a flare star. Its brightness can jump by a factor of 100 in hours, releasing massive bursts of X-rays and ultraviolet radiation. These flares have likely stripped away much of Proxima B's atmosphere over billions of years. They're also catastrophic for electronics. A spacecraft trying to study the planet up close would face repeated radiation spikes with no warning. Proxima B orbits extremely close to its dim star, probably tidally locked with one side in permanent daylight and the other in eternal darkness. Temperature extremes would be severe. The planet is nothing like Earth. Even if we could reach it, we'd find a world far stranger and more hostile than most people imagine. Everything discussed so far assumes robotic probes. Human missions aren't just impractical, they're impossible. The journey time alone rules it out. Decades in space mean food, water, oxygen, and psychological stability for a crew that can't hibernate. Humans age. They get sick. Without gravity, their bones and muscles deteriorate. Radiation exposure would be lethal. Outside Earth's magnetic field, cosmic rays bombard everything constantly. Over decades, the cumulative dose would kill the crew even with shielding. And shielding heavy enough to truly protect them would be too massive to accelerate. There's no return trip either. Anyone going to Proxima B goes forever. We can barely keep astronauts healthy on the space station for a year. Interstellar travel is orders of magnitude harder. If we can't go there, we observe. Modern telescopes are extraordinarily powerful. The James Webb Space Telescope and future observatories can analyze exoplanet atmospheres by studying how starlight filters through them. We can detect oxygen, methane, and water vapor. We can map temperatures and search for weather patterns. This isn't the second best. It's real science. Most of astronomy's greatest discoveries came from observation, not theory. We understood the expanding universe without leaving Earth. We mapped the cosmic microwave background from here. Distance forces patience. It filters out easy answers, but it also sharpens our questions. What we learn about Proxima B teaches us about planetary formation, atmospheric evolution, and the conditions for life. We don't need to walk on its surface to understand it. Proxima B is unreachable, not because we lack ambition or funding, but because physics sets boundaries we can't cross. The speed of light is absolute. Energy requirements scale exponentially. The universe is vast beyond comprehension. But unreachable doesn't mean irrelevant. Each observation brings new understanding. Every simulation teaches us something about how planets work, including our own. Proxima B serves as a mirror, showing us both the limits of what's possible and the power of what we can still learn. We might never stand on that distant world, but we'll keep watching it, studying it, imagining what it's like, because exploration isn't just about going places, it's about pushing against boundaries, even when those boundaries push back. Sometimes, the distance itself is the most honest teacher we have. If you found this perspective on space exploration eye-opening, there's more to discover. Hit that subscribe button to explore more mysteries of the cosmos, from black holes to the edge of the observable universe, and drop a comment below. Knowing we can't reach Proxima B, should we still try to send a probe? Let's discuss what's worth pursuing when the destination is beyond our reach.